prove the second part of theorem 1.9, because I bet you remember that thing, by proving that, and we have some sort of limit. So this is the one where the first part of it, the first part was the limit as x approaches 0 of sine x. That's a sine x, just trust me. Sine x over x is equal to 1. We proved that one with the squeeze theorem. And the second part of it is the one that the problem that we have right before us here, that the limit as x approaches 0 of 1 minus cosine x over x is supposed to be equal to 0. Okay, so let's just play like, hey, I'm just trying to evaluate this limit and see what happens. Okay, so if I plug in 0, across the top I'm going to have 1 minus cosine 0. Cosine of 0 is 1, and then of course I have 0 at the bottom. Ignore this guy for right now. We know it's supposed to be 0. But if I directly substitute in, I get 0 over 0, which is indeterminate, which could be a whole bunch of different things. We're just trying to prove that it's actually supposed to be 0. Okay, or at least approaching 0, I should say. Okay, so we have lots of tricks. We have rationalizing the denominator, or numerator, I should say. We have factoring and canceling out factors, and some sort of trig substitutions. But really, as far as the trig substitutions go, this is what we have. It's the sine x over x. I can't, just use this theorem to prove itself, and I don't see a sine x over x in it, so right now I'm kind of stuck. So really, this one, the way I'm going to do it is related to rationalizing the numerator. When you rationalize the numerator, you're supposed to multiply by a conjugate. And this 1 minus cosine x, you may remember from pre-cal when you've had to solve some trig equations that were kind of complicated. One of the things that you could do, one of the tricks, is multiply by a conjugate, and maybe it rearranged things for you. So the conjugate of 1 minus cosine x is going to be 1 plus the cosine x. That's what we're going to multiply by, the top on the bottom. So limit as x approaches 0, 1 minus cosine x over x, the original problem, we're going to multiply by 1 plus cosine x over, 1 plus cosine x. Which, this should be a fancy one. At least it is over some interval, which is what I want to rearrange the original problem. So across the top here, this is going to be like the difference of two squares where the middle term cancels out, and so it's pretty much just squaring the first term and the last term. So the limit as x approaches 0 of, and I'll have 1 minus cosine squared x over x, and I'll put this in parentheses, 1 plus cosine x. Okay. Now, again, let me just call your attention to this. I need to have, if I'm going to do some sort of substitution, I need to have this sine x over x, which I don't have, but I have something that looks like a Pythagorean identity here. 1 minus cosine squared x is equal to sine squared x. So I'm going to do that as a substitution. So I have the limits as x approaches 0. Ro, you want to say hi real quick?
Yeah.
And go ahead, say hi.
Hi.
There you go. Alright, so
I'm Rowan.
That's Rowan, correct. So I've got sine squared over x times 1 plus cosine x. Alright, now we're getting closer, because I can take this sine squared that's in the top here and then just make it a sine x times sine x and pair up one of them with this x that's in the denominator. So I've got limit x approaches 0 of sine x over x. That's taking care of one of these sine x's and this x that's in the denominator, times sine x over, that's the remaining sine x from the numerator, and 1 plus cosine x from the denominator. Alright, and then we had that theorem which basically says that if we could find these individual limits, then we can just multiply their respective limits together. Alright, so the first one here we proved in class with the squeeze theorem. That's 1, and here we should just be able to directly substitute this stuff in here. So the first part, sine x over x, as x approaches 0, also approaches 1. And on the top here for the second fraction, the sine of 0 is 0 over 1 plus the cosine 0 is 1. That's it doesn't really matter what the denominator here as long as it's not 0. 1 times 0 is 0. So check. We were able to prove the second part of theorem, whatever you want to call it, that the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Both of these things, that one and that one, need to be committed to memory.